I'm going to be talking about applications of derivatives. Using derivatives in various ways, such as finding local or global minima and maxima, is applicable to many problems. Among these are problems of optimization and related rates. Problems of these sorts are often found in sciences and economics. For example, consider the following problem. We have 40 units of fencing, and we can use this fencing to plot out a rectangular area, and we want to maximize the area that's surrounded by the fencing. So our fence could look like this, with maybe 2 units on each of these sides and 18 on these, or something more square like this, with 12, 8, 8, and 12. But our goal here is to optimize our values for the side lengths of this rectangle so that the perimeter is still 40, but the area enclosed is as large as possible. To solve a problem like this, we first need to determine what the variables are. Let's say we have length and width. However, here the length and width can't just be any numbers. We know that the total fencing we have is limited to 40 units. So the perimeter, which is 2 times the length plus 2 times the width, must be equal to 40. The next thing to do is to determine the quantity which we want to maximize or minimize. Here we want to maximize the area. So A of L and W is equal to L times W. The area is the length times the width. And finally, we have additional restrictions. We know that the length and width are the length and width of an actual fenced area. This means that they both have to be greater than or equal to 0. And since the perimeter is limited to 40, the largest either of these can be is 20. So they're also both less than or equal to 20. Now that we've set up the problem, all that's left to do is solve it. However, we don't really know how to maximize a function of 2 variables, which is what the area is. But we are given an equation that relates the 2 variables. So if we solve for one in terms of the other, then we'll be able to write the area as a function of one variable, which we can maximize. Let's do this. So 2w plus 2l is equal to 40. Let's solve for w in terms of l. If we divide this equation by 2 on both sides, we get w plus l equals 20, and then subtracting l, we get w equals 20 minus l. Now we can write the area as a function of only l. A of l is equal to w times l, which is equal to 20 minus l times l, which equals 20l minus l squared. Now to maximize this area, let's take the derivative to look for critical points. So a prime of l is equal to 20 minus 2l. Setting this equal to 0, we have 0 equals 20 minus 2l, so 2l equals 20, so l is equal to 10. We know that at l equals 10, we can solve for w, as w equals 20 minus l, which is also equal to 10. So the area is equal to 100. But we're not done yet. We've only checked the critical points where the derivative is 0. We have yet to check the edge points. Since we determined before that l is greater than or equal to 0, and l is less than or equal to 20, we have to check l equals 0 and l equals 20. At l equals 0, w is equal to 20 minus 0 equals 20, and the area is equal to 0 times 20, which is 0. At l equals 20, we have w equals 20 minus 20, which is 0. So the area is 20 times 0, which is also 0. Now this accounts for all the critical points. So the maximum must be here at l equals 10, where the area is 100. So the best way to set up the fencing is with a square.